Association and dataset expressions are the basic elements of a system in the Wolfram language for working with structured data. Associations can be constructed using the association function. For example, this input gives an association with 4 elements. The arguments in association are rules, where the left side of each rule is a key and the right side of each rule is the value associated with that key. Associations can also be entered using a less than character and a vertical bar at the beginning and a vertical bar and a greater than character at the end, so this input is simply another notation for entering that same association. Associations work a bit like lists. For example, this uses the part function to pick out the second value in that association. Unlike lists, however, values in an association can also be accessed using keys. This input, for example, picks out that same value using the corresponding key rather than using the position of the value in the association. The part function is commonly entered using double square brackets, so that input can also be entered like this. Values can also be picked out of an association without using the part function at all, and instead using the key enclosed in single square brackets. All of these inputs give the same result, so the choice of which notation to use is in principle a matter of personal preference, but for more complicated queries, the notation in the last example with the key enclosed in single square brackets is the most common and is typically the most convenient. Datasets can be built from associations in which the values are other associations. This input, for example, uses the dataset function to construct a dataset from an association of associations. As with associations, values in a dataset can be picked out either using the part function or using keys enclosed in single square brackets. For example, this uses part to pick out the value in the second column of the 4th row, and this uses corresponding keys to pick out that same value. It's possible to do a variety of other operations on datasets beyond just picking out values. For example, this uses the select function to select rows based on the value in column 1 of the dataset. The column can also be identified using the corresponding key. This input, for example, which uses density as the name of the variable in the pure function, gives the same result by selecting rows based on the value in the density column rather than based on the value in column 1. The select function can also be used in an operator form. This shows the equivalent input entered using the operator form of the select function. And when working with datasets, rather than entering the dataset as an argument of the operator can be entered in single square brackets after the dataset, so this input shows yet another way of getting the same result. The syntax using keys as the names of variables in pure functions is a general notation that works for any pure function applied to an association. For example, returning to the association introduced earlier, this shows a pure function applied to that association, and where keys are used as the names of variables in the pure function. For comparison, this shows an equivalent calculation with a pure function applied to a sequence of arguments without any keys. Variables in this input are identified by their position within the sequence of arguments rather than using keys. So number sign 2 refers to the value at position 2 in the sequence of arguments, and number sign 4 refers to the value at position 4. Being able to use keys as the names of variables is especially useful when working with datasets, where keys provide a way to refer to parts of the dataset using meaningful names rather than by their numerical positions within the dataset. It's worth noting that using keys as the names of arguments in pure functions will work only if the keys are strings. So far, all of the keys in the examples have been strings, but the keys can actually be anything. This input, for example, also gives a valid association even though only the first key is a string. The key that is a string can be used as the name of a variable, but trying to use other keys that way just generates an error message. A key that is a string can also be used in the part function to pick out an associated value. The part function is entered in this example using double square brackets. And any of the keys, including keys that are not strings, can be enclosed in single square brackets to pick out associated values. Keys that are not strings will work in the part function only if the key is enclosed in key. Otherwise, the calculation fails and generates an error message. In practical examples, the requirement that keys be strings is usually not much of a limitation, since the keys are just labels for parts of the dataset and strings provide a convenient and adequate way of representing those labels. Operations on datasets can be applied to the entire dataset, or to rows or columns, or to individual values, or at any other level in the dataset. For example, returning again to the earlier dataset, this shows map used to apply a function g at level 1, which applies g to the rows in the dataset. That same result can be obtained using the notation with operations entered in square brackets. This input, for example, uses the symbol all to apply G to all of the rows in the dataset. This shows map applying a function h at level 2 in the dataset, which applies the function to the individual values in this dataset. And this gives the same result, again using a different notation. This input applies h to all values in all rows of the dataset, which has the same effect as applying h at level 2. Several operations can be included in the same input. For example, this shows generic operations f, g, and h applied at different levels in the sample dataset. The same result can be obtained using map and explicit level specifications, but the notation with operations enclosed in square brackets after the dataset is more compact. That result shows how operations are applied at different levels in the dataset. The first operation after the square bracket, the function f, is applied to the entire dataset. The second operation, the function g, is applied to each row in the dataset, and the third operation, the function h, is applied to the elements in the dataset. That result also shows explicitly which keys are available to the functions at each level. For example, this input applies the function f at level 0 to the value associated with the key birch, which is one of the keys at level 0 in this dataset. If a named argument in a function does not match any of the keys at the level where the function is applied, the result is an error. This input, for example, generates an error because although density is a key in this dataset, it is not a key at level 0 of the dataset. This sort of error can be avoided by keeping track of which keys are available at the level where a function will be applied. For example, this shows an operation applied to all of the rows in the dataset, and for each row, the function g is applied to the value associated with the key density. The rows correspond to level 1 in this dataset, and density is one of the keys at that level. Many dataset operations map over the elements in their arguments, in which case the keys that matter are the keys at the level where the functions with the named arguments are ultimately applied, and not the keys at the level of the enclosing operation. For example, that same result can be obtained like this using a map operation that applies the function g. Although the overall map operation is applied at level 0 here, and density is not one of the keys at that level, map applies the function g at level 1, and density is one of the keys at level 1. That is also what is going on in evaluating this example, which uses the sort by function to sort the rows in the dataset based on the value associated with the density key in each row. The overall sort by operation is entered here as an operation applied to the entire dataset, and density is not one of the keys at that level, but the sort by function, like the map function, applies a function to its elements, and the elements in this case are the rows of the dataset, and density is one of the keys within each row. There are lots of other operations on datasets. This shows an operation called take smallest by, used here to get a dataset consisting of the rows from the example dataset with the two smallest values for density. Operations can also be combined in various ways. For example, this shows that same result computed by first sorting the rows based on density and then using the take function to take the first two rows in the sorted result. That calculation can also be entered like this, using the function composition operator /*. The /* operator is a special notation for the right composition function. Right composition applies functions from left to right, so right composition of functions f, g, and h applied to an argument x means to first apply f to x, then apply g to the result, and then apply h. In the dataset example, the sort by function is applied, and then the take function is applied to the sorted result. When there's more than one operation in the same dataset input, the system automatically chooses a suitable order in which to do the operations. For example, this input, which takes the rows with the two smallest values for density and then picks out the hardness column, works by first taking the rows with the two smallest values for density and then picking out the hardness column in the result. Doing these operations in the opposite order by first picking out the hardness column would not have worked, because the result after picking out the hardness column no longer has the density column needed for the other operation. The strategy that the system uses for choosing the order of operations is based on the distinction between ascending operators and descending operators. The operators in this example are descending operators, which means that when there is more than one operator, the order of applying operators is to apply operators at outer levels before descending to deeper levels in the dataset. Ascending operators are applied in the other direction, starting with deeper levels in the dataset and ascending to outer levels. For example, the mean operator and generic functions like f of density in this input are ascending operators, so f of density is applied first and mean is then applied to the result. It's always possible to do the operations in a different order by using separate steps. This pair of inputs, for example, applies the mean function and the f of density operation in the opposite order by first applying mean to both of the columns in the dataset and then applying f of density to that intermediate result. In the Wolfram documentation, the reference page for dataset includes lots of additional information on dataset operations in general and includes lists of operators and whether they are ascending or descending and lots of other examples of the many available operations. Before any of these operations can be done, of course, the dataset must first be loaded into the system. As an exercise in some of the issues that come up in getting data in and out of the system, consider first exporting and then importing the sample dataset from this section. This uses the export function to export that dataset to a comma-separated value or a CSV file, and this shows the contents of the file that was saved, which is a plain text file with commas between keys and values and records on separate lines. Importing that file directly will, by default, give the data as a plain list of lists. This list of lists, or any data in a similar form, can be converted with a bit of programming into a dataset expression. This shows one way of converting that list of lists into a dataset equivalent to the original. This input uses the association thread function, which is basically a combination of the association and thread functions for turning a list of keys and a list of values into an association. Another convenient tool for importing datasets is semantic import. This shows semantic import used to read the CSV file in this example. This gives the dataset as a list of records rather than as a table with labeled rows and columns. The key column 1 was inserted as a default key for the column that was not part of the original dataset. This input shows one way of replacing that key with a more meaningful label. It's also possible, again with a bit of programming, to reconstruct a dataset equivalent to the original dataset. There are lots of places to get more information on datasets. In the Wolfram documentation, there is an entire section with links to guide pages on data manipulation and analysis. And from the Wolfram documentation, there is also a link to a collection of workflow pages on working with data, with step-by-step instructions for importing data in various formats and for a variety of common dataset operations. Elsewhere on the Wolfram website, in the Wolfram function repository, there is a section with links to hundreds of functions that have been submitted for doing things with datasets, and the Wolfram data repository provides links to a broad range of datasets.